So today we have Jan Arlt, who's joining us from Aarhus University to talk about some experiments looking at beyond near field physics in quantum gases. So Jan, I'll let you take it away.
Thank you very much, Kali, for the kind invitation. It's a pleasure to be reporting on our experiments, and I will actually take a little detour and tell you a little bit more about Aarhus, and then start on discussing the experiments on the Lee-Huang-Yang correction. Yes, so for those who are in Glasgow, we actually share almost the same latitude, 56° north. Aarhus is over here on the right, and Glasgow is on the left, just to give you a bearing where we are. Aarhus is actually the second biggest city in Denmark, with about 300,000 people, and it has a very nice campus university right in the center of town. So I actually sit in these buildings, if you can see my mouse here right now. As I was just telling Kali, all restrictions have been dropped and we are back to normal in Denmark, which is really quite amazing. Okay. Feel free to interrupt me at any time. I'll be happy to answer questions also along the way. So the overarching theme of our group is the control of many-body systems, and to find out more about the sort of inner workings of these many-body systems. And this comes in many different flavors. We have experiments on mixed systems, which is what I will be talking about in some sense today. The particular case which has taken much of our attention recently have been the case of very few impurities in a quantum system, which leads to the formation of polarons. And then we've also investigated molecular physics and Efimov type physics. We do that on two experiments. The one which we call the mix experiment. It's originally an apparatus that cools both potassium and rubidium to quantum degeneracy. And that's the one I will mainly be talking about today. However, we also have a second apparatus, which we call the lattice experiment, mainly for historic reasons by now, because the recent experiments which we've done there have nothing to do with lattices, but rather with the fundamentals of BEC. Let me just mention that very briefly before I go ahead and talk about the LHY work. So when we think about BECs, we usually think about a static proportion of thermal atoms and BEC atoms. But that's not actually true. As you see in my cartoon here, atoms can actually hop from the thermal cloud into the BEC and out of the BEC. And this has to happen in some sort of intricate balance between these hops that preserve energy. And these were predicted really in the 60s and have never been observed, and have been a long-standing puzzle. So I want to promote a little bit the work we've done on these fluctuations, where we've observed that as one lowers the temperature from the right to the left here, one actually sees a sudden increase in fluctuations between the BEC and the thermal cloud as one crosses the critical temperature. And then there is a maximum up here in our data. And after that, as more and more particles populate the BEC, these fluctuations die out again. And beyond the sort of interest in the fact that these BEC to thermal ratio is not a constant, as we often assume, there's actually an interest because it tells us about the statistical ensemble to be used when describing BECs. So the textbook calculation everybody makes is in the grand canonical ensemble, which actually does not show these fluctuations at all. But whereas canonical or microcanonical calculations actually show them, and we show that the microcanonical ensemble is actually the right ensemble to calculate for the BEC. Moreover, that was just a very sort of quick advertisement of the work going on that experiment. On the mixtures experiment, the work that actually led us onto the LHY investigations has been the investigation of Polaron physics, which is actually performed in a very similar region to what we are investigating today. And I will therefore take a little detour to that field. So the Polaron is actually quite a typical problem. It's the problem of an electron which travels through a solid and deforms the lattice. And in that sense, it sort of drags phononic excitations along with it. And those phononic excitations can actually be mimicked by the quantum gas, because phonons, just as Bogoliubov modes, can form these polarons. So we actually have, despite the fact that we don't actually implement a lattice in these experiments, we have quite a good model system to do quantum simulation of the polaron. And the sort of basic experimental sequence towards those goals is actually the same one that we're using for the LHY physics. So let me describe that in both cases. Our apparatus is a dual species apparatus. So we have a dual species mod on the left here, in which we collect both potassium and rubidium in a magneto-optical trap. After doing so, we ramp up the current in a set of coils, and these coils are movable, so they actually then move over to the region where we want to conduct our experiments. And there we have an angled glass cell, and we transport these atoms into this far angle of the glass cell, where we now have access from four different, well, all 6 different directions to our little cloud of atoms. We selectively then cool the rubidium. So for all of what I'm discussing today, rubidium is just a coolant. So we actually throw it away after a little while. So we first cool rubidium in the quadrupole trap. We then deform the trap into a quick type. You have a Pritchard trap. Evaporate further before throwing away all the rubidium and transferring only the potassium, in our case potassium 39, to an optical dipole trap. And that is the starting point for both the work on polarons and the work on the LHY fluid discussed today. Potassium 39 is nice in the sense that it has an interesting Flashback structure, which enables all of this work. And in particular, the lower hyperfine manifold has the structure shown here for the f=1, mf=-1 state. So that's the blue line. It has a negative background scattering length, so you can't condense at low magnetic fields. That's the blue line here. But then around 50 Gauss or so, it has a Flashback resonance, and then there comes a broad valley. And this broad valley allows you to condense both on the left-hand side and on the right-hand side of the valley for potassium 39 in the 1-1 state. We will be discussing a region that lies in this 50 Gauss region here. So we will be discussing work that is performed at the left-hand side of this valley when we discuss the LHY fluid. For the purpose of the work on polarons, however, we use yet another Flashback resonance, which is shown in green, in the green dashed line here. And this is an interspecies Flashback resonance between the 1-1 and the 1-0 state. And this allows us to make extremely strong interactions between 1-1 and 1-0 atoms. And if you do that, then you have formed such a model of an impurity, a very small amount of atoms in the 1-0 state, which strongly, either attractively or repulsively, interacts with the remaining cloud. And it can be attractive, as shown here, or repulsive. And in that case, you form the polaron, whose energy is shown as an orange line here, as a function of the inverse interaction strength. And you have both an attractive polaron and a repulsive polaron. And we've actually mapped out these energies in the past. So this is an energy diagram for that polaron case taken in 2016, so already quite a while ago. But what I want to advertise here is that we have actually only recently been able to observe the formation of these polarons using a Ramsey type experiment. And that was published in Nature Physics in 2021, so just last year. So that's an investigation which we continue and which really prepared us for investigating the LHY fluid, which I'll be talking about today. Okay, so that was the prequel. As you know, the Lee-Huang-Yang fluids came back to the community's attention with a paper by Dima Petrov published in 2015, where he explained that the competition between the LHY term and the mean field term can lead to the formation of droplets. And this was quite a revelation, because it explained some of the ongoing experiments in dipolar gases, which had seen similar effects but weren't fully explained. I don't want to go into that direction, because it's really a direction of its own. But just point out that the original proposal by Dima was actually exactly for the system that I've been talking about, namely potassium-39 in the two states, 1, 1, and 1, 0. And the person who sort of took that most serious, or was the first one to take that very serious and design an experiment, was Leticia Taurel from ICFO in Barcelona, as well as the Florence group. And they showed that such droplets, which are self-stabilizing without the need for a trap due to the competition between mean field and the LHY interaction, can be formed. Now, we realized that our trap wasn't ideal for that particular case. And so we were looking, we were actually intrigued by using that technique, but we didn't want to go exactly in the same direction. And this actually prompted a student of mine, Niels Jørgensen, with help from the theoretician here in Aarhus, Georg Brun, to investigate a slightly different case. And that is the case where we cancel the mean field interaction completely in a dual species case. So rather than sort of compensating for each other such that there is some remaining overall mean field, which then together with the droplet together with the LHY leads to these droplets, we asked ourselves, can we completely get rid of the mean field and observe the LHY effect only? And that led to this publication shown on the right here in 2018, and that was the basis for our work published last year, shown here. So what is it we are trying to achieve? Well, we are trying to isolate the LHY correction term, which is the first beyond mean field correction to the Bose gas, and that was sort of first predicted in 1957 here in this paper by Lee-Huang and Yang. It originates from the 0-point energy of the Bogoliubov modes in the system. And therefore, these are often called quantum fluctuations of the Bose-Einstein condensates. In our case, obviously, we can't sort of just turn off the mean field. Well, we could if we use the zero crossing provided by Feshbach resonance, but it turns out that the mean field term scales with the scattering length as well. So if we just went to zero scattering length, then we would be turning off the Lee-Huang-Yang term alongside with the mean field term, and both would be very small. So that doesn't work. So we have to take a more clever approach, and that's the approach sort of first suggested by Dima Petrov. So what do? Well, we have our two different states, atoms in state 1 with density 1 and some scattering length between them, which has to be positive in order to be able to make a BEC. Same should be true for state number 2, where we again have a density N2 and again positive scattering length between the two, allowing us to make BEC in that state as well. However, we can have a scattering length between the two of them, which could be negative. And if we choose a negative scattering length here, we can arrange it such that the overall interaction strength is 0. So the relevant scattering length difference to look at, delta A here, is A12 plus the square root of A11 and A12, and that should be 0. And in that case, we compensate the scattering, we compensate the mean field interaction. And in a joint description of both states, the mean field term will actually drop out of the Gross-Petevsky equation. There's a small caveat here. This is only true if we also adjust the densities correctly. So we have to also match the densities to each other. So here is the required density between N2 and N1. Now we do all that in a type of single mode approximation where we assume that both N1 and N2 have exactly the same shape, so they overlap precisely, and therefore this also corresponds to a number balance between the two of them. Okay, so let's look a little bit at the theory done here. This is the energy functional that we usually know, only including the mean field. And if we arrange now for these conditions to be true, then this term, this mean field term here, drops out. And if it drops out, the next relevant term becomes important, and that's the Lee-Huang-Yang term, which I've now included here. And you can see now that it scales differently, right? Here with the wave function to the 5th power. And if we translate that, I'll translate that to the GP formalism. Well, it's translated to the GP formalism here, where you see our new type of Gross-Petevsky equation. It's obviously not the Gross-Petevsky equation anymore, but the mean field term here is now replaced by the Lee-Huang-Yang term. And the wave function here is now the wave function for this identical wave function for the two components. And you can see here that if this worked well, that would be quite nice, because we have played with this term for the last, well, you could say 25 years, right? And now, instead of having the density here, so the wave function squared, you have the wave function cubed. And you could wonder, well, can I repeat all experiments done in the last 25 years? And what consequences will this have for superfluidity? What consequences will that have for many experiments done with bulk condensates? And that's obviously what we're interested in. Unfortunately, it turns out not to be quite so easy, and I'll tell you why. So as I already indicated, we are using the same two states. We're using the lower hyperfine manifold of potassium-39, which obviously has 3 MF states, of which we use 2, because the GF factor is negative. The upper one is the uppermost, the low field seeker, is F equals 1, MF equals -1, in which we make our BC as described before. And that we do at the sort of left-hand side of the valley that I outlined before. So this here is the red line here is now the left-hand side of the valley of positive scattering length, which I described before. And then there's a Flashback resonance which I hadn't shown previously for the MF equals 0 state here at about 60 Gauss, and that's shown in green. Actually, there are 2 Flashback resonances close to each other, but this part is relevant. And moreover, we have a relatively flat negative scatter length between the two of them. Right? So that's the dashed blue line here. And now we can ask ourselves, where is the condition that I indicated before fulfilled? Well, that is the case here at a scattering at a magnetic field of 56.8 Gauss. And at that particular point, indicated by the dashed vertical line here, we have a positive scattering length of 33 Bohr radii for the 1-1 state, 84 for the 2-2 for the 2 state, and the negative scattering length between the two of them. So here is the point that does it for us. And if you now plug in, you see that we actually need 40% of the atoms in the 2 state here in order to also fulfill the relative density criteria. Right. So that's the place where we want to be, and that's where the place where our LHY fluid should be. So so what will be our probe? Our probe will be collective excitations, because they can be strongly dependent on the interactions in the condensate. Let's look, just as a reminder, at the mean field case, which is been well known for decades. If we have a trap with an oscillation frequency omega naught, and we have a non-interacting gas, then we know that the oscillation frequency will be exactly twice the trap frequency, and that's shown when that should be the case when our interaction strength here on the x-axis is exactly 0. And that's indeed the case for the so-called expansion mode, right? Or the monopole mode here of the BEC. And then for positive interaction strength, then the frequency of oscillation rises. The contrary is, or similar behavior is the behavior of the quadrupole mode, shown here in green. So again, that also has exactly the frequency of 2 trap frequencies at 0 interaction strength, and then decreases. However, the quadrupole mode is not particularly useful for us because it only depends weakly on interaction strength. So we'll be using the monopole mode on the left here as our tool to investigate. And what's the limit of that? Well, if we increase the number of atoms, this goes to about square root of 5 omega naught, and whereas the quadrupole mode goes to square root of 2 omega naught. Okay, with that in mind, we can now start to compare to the LHY fluid. And this is the calculation we had done previously in 2018. It turns out that the relevant parameter for the interaction strength in the LHY fluid is this one here, which is mainly determined by this interaction strength between the two samples. And as you can see, my axis now slightly offset. We have the limit of square root of 5 omega naught here as a dashed line. So that would be the limiting value for the BEC case. And you can now see that for the LHY case, the frequency of oscillation is actually goes towards a value that is considerably higher than that. And that's because as we only have the LHY fluid, the sample becomes much slower and much smaller, and actually quite a lot stiffer. And the limiting value of the oscillations of the LHY fluid will then be square root of 13/2 times the trap frequency. And that was all shown in our first 2018 paper. And we were actually hoping that, fantastic, now we just go to that point and we make that observation and we'll be happy. And we'll have shown that if we follow with our data this red line, then we should be good. However, it turns out to be more difficult than that. So from now on, I will be using this interaction parameter U here, which is actually a dimensionless interaction parameter, which characterizes the strength of the LHY interaction with respect to the kinetic energy, and sort of in a sense replaces interaction strength for our case here. So here is the comparison between the two cases, right? So this would be the blue line is the line of a normal mean field BEC and its limiting value of the oscillation strength, and the red line is now our LHY fluid. Right? They don't have, this is a sort of fudge, right? This is just a cartoon in the sense that the interaction parameter here, the x-axis, is not actually the same. It's just supposed to give you an impression of what we want to investigate. And the important thing is that we are actually not sort of looking for a difference between the red and the blue line here, because the blue line will be 0 always. We will be 2 always. We are always working in the situation where we have actually no mean field interaction present. Okay, so now I told you that our tool will be the monopole mode, and the monopole mode actually tends to be slightly tricky because as you poke or push your BEC, you usually tend to excite the quadrupole mode. It tends to be easier to excite, especially if you have a trap that is not completely symmetric. So the first thing we had to do in order to do experiments was to produce a spherical trap. And in our case, again, here you see the cell in which we do our experiments. This meant that beyond the two trapping beams that we already had, which are laser beams at 1064 nanometers, we actually had to include yet a third beam in order to really be able to tune the trap to be spherical. There's actually it would also be possible with 2 beams only and the use of gravity, but that would restrict ourselves to a very, very particular trapping frequency and a very loose trap. So we included a third beam to have both tight traps and the ability to make them spherical. Okay, so once you do that, you obviously calculate what the waste, the waste, you've measured the waste, you calculate what the powers in your beam should be, and then you put those in and you measure trap frequencies. And when you measure such a trap frequency, you actually get a measurement like this on our 2 cameras. So this is the left-hand side is imaging along the x-axis, and the right-hand side is imaging along the z-axis. So there's actually a direction here, the y direction, which we see on both cameras. And it looks very messy. And then you realize that you've made a very, very round trap now. And once you've made a very round trap, the question is, which are suddenly the principal axes of your trap? Even small deformations will now, as you are quite spherical, lead to shifts of your principal axis of your trap. And that makes it quite annoying. So rather than looking in the reference frame of your cameras, you now have to ask, what are the principal axes in the frame of the atoms or in the frame of the trap? And what you can do is you can actually transform with a set of rotation matrices to the reference frame, from the reference frame of the imaging system to the reference frame of the trap. And you can include that angle of these angles, theta x, theta y, and theta z in your fit. And suddenly you see that, well, there are trapping frequencies after all. With the guiding line, you realize, well, this actually makes very good sense. So you measure your trap frequencies like this. You then have to, you then realize that obviously the trap frequencies aren't all the same or aren't quite close enough to each other. And then you correct afterwards for the powers in the 3 beams. And that's an iterative process involving many of these fits. And finally, you come to you reach a set of powers that gives you a very good spherical trap. Good. Once that's done, we can get started on making our LHY fluids. So what would you think you should do in the ideal world? Well, one should prepare BC in the first state. Then one would like to transfer 40%, that's the number we came up with for our particular scattering length configuration, into the second state. And then we would like to perturb the potential very slightly in order to excite oscillations. Now these oscillate together as a joint LHY fluid composed from the two interacting BECs, and then we would image. Unfortunately, this is not possible. Inelastic losses are the big problem in our experiments, in particular inelastic losses in the state number 2. So the F equals 1, MF equals 0 state has a very large loss rate. And that impedes us from nicely producing a mixture and then gently initiating these oscillations. Instead, what we do is the following. We prepare again a BEC in state 1, and we then go to the point where delta EA should be 0. But we're only in the one state right now, right? So we just move to the right magnetic field no more. And then we use a very short, in our case, 1.3 microsecond duration RF pulse to create the atoms in the state 2. And this is very violent for the BEC. You've suddenly transferred 40% of the BEC atoms very violently in a different state, and at the same time, you have actually taken all the mean field energy out of the system, right? Or at least compensated for it through the balance that we've taken. And that means that suddenly there is no more mean field overall in the one component framework. There is no more mean field energy, and the BEC or this LHY fluid will start to quickly contract, right? So this in that sense, our pulse now produces the LHY fluid and initiates the oscillations at the same time. Okay, so then we let this oscillate for a little while. We do a time of flight with a magnetic field gradient in order to do Stern-Gerlach separation of the two clouds, and then we obtain images like this here, which are now images of the atoms in our two different states. We fit to these. Here you see the fit function that we use. It's an empirical function. It's essentially a sinusoidal, but we've added an offset, we've added a slope, and we've added an exponential decay. And what you see here now are on the right-hand side are graphs for the two states. The upper one is the one state here, the lower one is the two state. And you see a number of nice features that are sort of what we expect for this joint LHY fluid. First of all, in both cases, in the one and the two state, both the X and the Y direction, now shown as red triangles and blue dots, oscillate together with each other. So this indicates that these really are monopole oscillations, because if we had quadrupole oscillations, these would be out of phase with each other. Secondly, we see that the two clouds oscillate in phase with each other, as we expect for a joint LHY fluid. Pardon me. However, we also see that towards the right-hand side, the oscillations already damp a little bit in the two state, and that means already after a few oscillations, we must be moving away from the balance shown up here. So we only retain the LHY fluid really for a few oscillation periods, and the reason for that is sort of twofold. It's the loss in the two state, but it's also the fact that these oscillations are violent. If you look at the y-axis here, you can see that we started out with a radius of about 100 micrometers, but then the BEC is halved in size and then expands again. So these are quite drastic oscillations. So honestly, when we did these experiments first, we sort of hoped that these would agree with our previous theoretical treatment, but that was not the case. So we had to go beyond that, and we actually had to do some calculations ourselves this time, because we had to include all the nitty-gritty detail that the experiment involves. We did that in gpelab. I don't know if you are if you use that. This is a MATLAB toolbox available at this address. It's public domain, and all you have to do is cite its creators. And it's nice because it allows you to do a two-component simulation, and it allows you to include further terms. So you can we just included the LHY term ourselves. But because we wanted to include losses, this sort of one-component framework that Dima Petrov had introduced was not enough. So we actually had to go back to the two-component framework for the detailed simulation. And that's shown here, right? So I and j are the I being equal to 1 or 2 are the two components, right? And then we have the mean field interaction, and we have the LHY interaction, and we have the cross terms between them. So what does that involve? Let me just very briefly run you through the complexity of this simulation, which was done by my PhD student Thomas Sko, who did a fantastic job at that. So here is the Gross-Pitievsky type equation that I showed before. Here you have the mean field term, which now includes both of the densities. So there is a cross term for each of them. The LHY term actually becomes quite nasty when you write it down for both components. You can see here that there's actually a sum here over both the plus and the minus, and then you have all the different scattering length and densities involved. But that can be put into the GPE lab framework, and that's what we had done for the 2018 publication. What we had not done for the 2018 publication was to include losses as well. Right? So we have losses due to the formation of molecules, so three-body collisions that lead to the formation of a molecule, which is then lost, and the loss of the third partner in that collision. And these three-body losses are typically characterized by this K3 loss coefficient times the density squared, and that leads to decay, as one would show from such an equation. So we include all loss channels here. So they're given here. So this is the loss channel between 3 atoms of the same state, 2 atoms of the same and one of the other state, and vice versa. So all these loss channels are involved for both of the mixtures. So you put all that together in gpelab, it becomes quite cumbersome. But again, Thomas did a huge, a fantastic job on that, and could then simulate the case. So what does he do? Well, firstly, we calculate a single component ground state wave function of the BEC in our first state, and then we simply copy that state into a second one and adjust the relative numbers in order to match our 40% in the state 2 requirement, and we adjust the scattering length appropriately. So all that can be done. And then we can perform dynamical simulation for this two-component system and obtain their oscillations. And this is the quite an instructive result of the oscillations. On top, we see the case without losses, right? And in that case, we just see oscillations which are not quite sinusoidal due to the interaction and the large interaction strength. However, when we include losses, which is the case for the lower 2 panels, something more drastic happens. The one state sort of behaves as if it had no losses on this time scale, right? We're looking at 12 milliseconds here. So that's largely unaffected. But the loss is almost an order of magnitude, 2 orders of magnitude larger in the 2 states. So that actually suffers considerable losses, as shown here. And not surprisingly, the losses occur exactly when the cloud is most compressed. So we see a sort of step function like loss down here for the two-state, which suffers from huge losses exactly at the minimal points when the cloud is most compressed. So already from this one can see that we adjust our system to fulfill the ALHY condition initially, but we are going to move away from that by default. Yes, so again we see large amplitude oscillations. We see an initial joint oscillation, and then we see slowly increasing mean field contributions. Good. So with that, we can now do a much more sophisticated simulation, which is shown in the following. So the red line was the one I had shown before. This is the limiting line for an LHY fluid, which starts from 2 and then goes to this limiting value for the case of large interaction strength. And one should remember that we are sort of comparing what our real comparison is the non-interacting limit, because our sample by default, if there was no LHY term, would be non-interacting. We've cancelled all the mean field interactions. So really the comparison for our experiments is the dashed line here. So then we have to include the preparation method. And as in any sort of driven oscillating system, huge oscillations have an effect on the oscillation frequency, right? And so the experimental preparation, so the detailed inclusion of the experimental preparation method actually means that our oscillation frequency is changed and moves down here to the green line. We then also include the losses. And again, that leads to a decrease of the oscillation frequency now, and thus now our expectation for what we are looking for the actual oscillation frequencies in the system is the blue line. This is still this is a little bit less clear signal than the red line, but it's still quite distinct from the non-interacting case, which lies down here. Okay. These are the same lines, just shown slightly differently, where I've included a third line, which is the one down here, where the losses were even doubled. So again, this is the non-interacting LHY case. This is the LHY case without losses, the LHY case with losses, so that's our expectation, and the LHY case with doubled losses. So that's the sort of area we're looking for. And now we can start to put in the frequencies obtained from our experimental fits. So when we use this empirical damped sinusoidal fit here, as shown in black, we extract a fit frequency. We do that many times, and we finally get this result, which we think agrees nicely with the full simulation of our case. I should add that we vary the interaction strength, so this parameter U, primarily by changing the number of atoms in the BEC initially. So we load different numbers of rubidium atoms and thereby potassium atoms, and thereby obtain different sizes of Bose-Einstein condensates. And we also try different trap frequencies. So these should be, obviously be taken care of by dividing by the trap frequency omega naught here. So the diamonds, squares, and circles represent slightly different trapping geometries, all of which are very close to spherical. So we were very happy with that result, because it really shows that we have a relatively stable LHY fluid, which we understand well in this detailed simulation. However, there's also the caveat that we also learned that it doesn't live very long due to the decay of the two-state. One could also ask what happens if we didn't choose the magnetic field quite right. So we have to hit a narrow window of magnetic field here as I indicated, around 56.8 Gauss in order to fulfill our balance of scattering length, and that obviously comes with an uncertainty which is due to the modeling of the Feshbach resonances. And we have included that arrow here as a gray area, which is nonetheless quite small. And we can, as a first comparison, we can ask ourselves, what would happen if we did not have the LHY term at all, right? And if we didn't have the LHY term, obviously we would be moving from, on the right-hand side, a repulsively interacting total BC to something where the attractive interactions are predominant on the left-hand side. And this is essentially what you do when you form droplets. You're also going that way. And if we didn't have the LHY terms, well, then we would observe a collapse, right? And that's shown in orange here. However, when we do include the LHY term, then the mixture is actually quite stable across this region because it's stabilized by the LHY term. And as we move to the very left-hand side here, we would be moving towards the droplet regime where the competition is a different one. However, we hold ourselves to this delta A equals 0 regime here, where we have the pure LHY fluid, and all our experiments were essentially performed within this gray region here. However, now we vary delta A by varying the magnetic field, and we observe that actually our experiments are very weakly dependent on the precise magnetic field we choose. And that's obviously nice because it sort of really means that our system is quite stable. And that's expected on the right-hand side in comparison with our theoretical calculations. On the left-hand side, it's really the fact that the growing effect of the negative scattering length really pushes then these two limits based on the different strength of the decay of the two-state quite far apart, and it's really hard to say whether or not how well we agree with theory on the left-hand side. Nonetheless, we're happy with the result in the middle. Great, and with that, I'm almost done, sort of roughly on time. I hope I've shown you that we have really developed a detailed understanding of the LHY fluid in our case, that we can realize an LHY fluid, at least for a few oscillation periods, unfortunately then decays into something that is more mean field like. But there are other systems and their prospects for this work that lend themselves to further investigations. There's work being done, and I think this has come out now, sorry for not replacing the archive link, in France on a coupled system. So you could ask yourself what happens when I do not only preserve the number of atoms in these two states, but when I continuously couple them with a Rabi couplet. One could go to a different set of scattering length, in our case at 381 Gauss, in which obviously the losses will be different. So that would be an interesting way to go. A fantastic prospect may be the potassium 41 rubidium 87 mixture investigated in Florence, for which LHY droplets were observed, and they should also lend themselves to these LHY fluids, and losses are much less dominant there. So that's this link, that's this citation here. One can also go to different trap geometries or higher order oscillation modes. We have only numerically simulated the quadrupole mode, which as we expect turns out to be much less dependent on the interaction strength, and therefore to be a much less interesting probe for us. And ultimately, it would be fantastic if one could look beyond the LHY term, although that may be difficult in our system, or to perform quantum simulations using the sort of quartic nonlinearity, which you get when you replace the mean field term, as we did with the LHY term, and therefore don't have density here, but the cube of the wave function, and therefore get an overall quartic nonlinearity in the GP equation. And that would start the game over for at least some set of experiments. And with that, I'm finished. Let me point out that this appeared last year, as I showed previously, and that much of this work was done by Thomas on the left here. The experiment has now been taken over by Anas, and the experiments on the fluctuations are done by Toke. And with that, I'm done. Thank you very much.
Thank you very much for an excellent talk. And if anyone has questions, please raise your hand or pop them in the chat. I'll start us off with one, which is I'm quite curious about the prospects for seeing beyond LHY or signatures of beyond LHY physics. You mentioned it would be challenging in your system, but maybe you can speak a little more about it.
Yeah. So once you can sort of control this term here, right? You can also wonder whether how large or small the next term is, right? And the problem is that the term has only been calculated in a single component gas. So I mean, there's a sort of theoretical challenge in the first step to extend that to two component gases, and therefore get a hold on the possible size of such next order terms. And once you do that, you can wonder whether you can now work out a system in which you reduce this term to a size that's low enough to observe the next order term, or to find a probe that is actually sensitive to the next order term. So that would be nice, but I think we are a little way away from that.
Fair. Yeah, whether things get progressively smaller as you go further out. Right.
But I think the prospect for these systems investigated here in Florence, for example, right? They are quite nice, and you know, droplets of the heteronuclear droplets have been seen there, so that's a very, very similar regime.
Right. All right. I believe Stephanie has a question. If you want to unmute yourself.
Yeah, thank you. Well, this is fantastically interesting. Thank you for a wonderful talk. I have the question about reducing the dimensionality. Have you thought about that? I mean, there's LHY sign, there's a sign change when you go to 1D, and but I guess you could do the same thing.
Yes.
In the absolute LHY limit.
Yes, yes. The reason why we have we've been careful about that is because it becomes quite difficult to distinguish in 1D between sort of solitonic behavior and the behavior of these gases. And Laetitia has written a nice paper on that, on the sort of crossover between solitons and droplets. And in addition, our particular probe here, the sort of monopole mode, doesn't work out very well in 1D. Sort of you by default always excite the quadrupole mode. The quadrupole mode really doesn't show the sort of striking dependence on the LHY term. So I mean, it would be fantastic to do that, but I don't know how to do it right now.
Because then in 1D, I mean, one has the possibility to study the persistent currents of this, presumably to a large extent superfluid system.
Yes.
So that would be very interesting to see the differences to a one component Bose gas.
Yes, and sort of this is a question we have been discussing, and to which I have no sort of answer. Are there, you know, in principle, if you take a sort of a Landau superfluid criterion, it all works out, as far as I can see, quite similar. Whether or not you have a sort of, this was actually to my surprise, honestly. I thought, well, if you now had a system where the nonlinearity was a completely different one, what would it do to the superfluidity of the system? Would that be very different? And it turns out that it doesn't seem to be. Sort of these the criteria for superfluidity are really quite similar. Nonetheless, sort of one could ask, well, what sort of quantitatively, which effect does it have? What is the new, what are the, what's the equivalent of the healing length, and what's the speed of sound, and questions like that. That would be very interesting to work out. And I don't think it's very difficult, but well, it'd be nice to investigate.
Well, thank you.
All right. I don't see any other questions in the chat just yet, but I have a more technical question, which is, can you remind me what the size of the droplets, or sorry, of the cloud is in the system? I suspect the data you were showing was maybe an expansion image, but I'm curious what the actual size of the gas is.
That's a number which. Let me see, is it not, when if I go back here to the simulated values for the simulated data, right? We don't include the time of flight expansion in the simulated data, right? So here you have the answer in a sense.
Okay, yeah, I see it there.
So sorry, because obviously that's the big difference between right and left here, right? So we can't include, due to the sort of changing grid size, we can't include time of flight in our simulation, and that's why there is actually a factor of pi between the phase of the simulation, which is done in trap, and the time of flight data on the left, which is out of trap, right? So we're imaging the momentum distribution, and that means sort of what was small then becomes large, and vice versa. And then the actual sizes are given here, so you can see what the simulated RMS radius is here. And this is always after fitting under the assumption that we have a Thomas Fermi distribution. So this is sort of also, let's say, an approximation to the size.
Right.
So this is sort of, that's the case for the numerics as well, right? So even in the numerics, right, because we do this sort of numerical Thomas Fermi, this numerical GP simulation on a grid, we also have to extract sizes there by making a fit, and that's what's then that results then into the data points shown as a line here.
Right. Okay. Thanks. That makes sense. Yeah.
Yeah, and I cannot sort of overstate my fondness without honestly being able to sort of do it myself on a daily basis of this computational tool here, the gpelab, which sort of offers various methods for solving the GPE equation in MATLAB relatively quickly with different tools to find the ground states, or to use to simulate the time evolution, and in 3D on a desktop computer. This was not, it ran for some of these simulations ran for a few days, but they ran on a little desktop machine.
Okay.
So that's really quite a nice tool, and allowed us to do this ourselves, and thereby sort of really tinker with these, with these loss coefficients and the trapping frequencies and so on. And obviously that code we wouldn't be able to write. Many theory groups have written their own code for that over the last decades, I'm sure, but we wouldn't be able to write a good and fast code for that in 3D.
Well, yes, as an experimentalist, I'm always on the lookout for nice code to borrow and cite.
Yes, and that's possible here. And then they have a bunch of nice examples. So you can just get started there. And if you had a particular interest in our simulation, including all these effects, I'll be very happy to share that.
Okay, thank you. Stephanie, did you have one more question?
Just a short one. Since we discussed this code, but it would be much harder for long range interactions, right? I think the fact that it can be so fast and efficient is probably because of the short range nature.
Yes. This is only including short range interactions.
Yeah.
I think you would, I'm not even sure whether it would allow you to do sort of to change the nature of the interactions. No, we don't we don't do that. You know,
because it sounds pretty amazing, because I mean, also for contact interaction, when you do 3D, I mean, you really need to get good convergence. You need a lot of mesh points, especially when you have a spherical trap on a square grid and so on, and then feeding everything into MATLAB. That sounds to me like a miracle.
Yes. I mean, honestly, we did not dig. Obviously, we trusted this code, right? We did the usual of when you use such a package. You know, we ran it for all the known cases that we could think of for the normal condensate with mean field interactions and so on, and checked that everything checks out, that everything sort of behaves as we would expect it. But obviously, we didn't go beyond that in sort of looking under the hood of how it works.
Yeah. It would be nice to look at it and have a race of codes.
Yes. Go ahead. I mean, these are two. Honestly, I forget now where they come from. These are two French mathematical physicists who provide the package, and you can just go and download it. Hopefully, now we've sort of, my students and I, or in fact, the department as a whole, is moving from using MATLAB to Python. So maybe I should write to them and ask whether they could provide a Python version.